All right. Well, hope everybody's doing well, social distancing themselves and feeling healthy. Today is our sort of first online lecture. We'll see how this goes. I've decided to start recording them in 10 to 15 minute chunks, maybe some a little bit longer, so you can watch them, go away, come back, and rewatch them whenever you'd like. So the first topic we're going to deal with is linearly increasing loads, and here we are back to moment diagrams. We actually have two topics left to discuss with moment diagrams. It's this one, and then what happens when we incorporate a release. So let me put a problem on the board here, or whiteboard, whatever. So it looks something like this. So we have a linearly increasing load. I guess I have a fixed support on this side. The way we are going to define the linearly increasing load is as a force per length. And it's actually the force per length at the maximum end. So that's kind of the defined as the amplitude. And we're going to define this as the length, like that. So the first step, this really isn't any different than uniformly distributed loads. But the first step here is to solve for, well, actually here it's a cantilever, so we don't have to solve for a reaction. So we can simply just take a cut. So I'm going to take a cut at some distance from the end. We're going to call that distance x. So, in fact, I'll call it x1. So the value of, this is just geometry, but the amplitude of the distributed load is actually W times x1 over L, right? So if x1 equals L, then we're back to the full W. And if it equals 0, then we're at 0, and so forth and so on. It's linearly varying. So here, the first thing we're going to do is apply our, replace the rest of the structure with our internal forces. So these are our V of x1. And these are our M of x1. Again, these are associated with the local sign convention that we have talked about. So now we're simply going to apply some of the forces in the x direction and some of the moments in the z direction. Sorry, some of the forces in the y direction, some of the moments in the z direction. And if I do some of the moments here, we're always going to do it about the cut, right? We're going to do a right-hand rule. We're going to say that equals 0. And now we need to replace this linearly increasing load with a load that is sort of located at the centroid of the linearly increasing load. It's a triangle, so this is going to be located at, let's see, 1/3, or we'll call it x1 over 3. Let me do that again. x1 divided by 3, right? So it goes through the centroid of the triangle there. All right, and its magnitude right now, we're just going to call it P, but I'm going to solve for that in a second, right? So some of the moments about that point, we're going to get P times x1 over 3, right? And that is positive because it's consistent with this right-hand rule there. And then I'm also going to get a plus m of x1, and that has to equal 0, right? And the p now basically becomes, I guess we'll try to go up here, the P becomes basically 1/2 base times length, right? So that's 1/2. The base is x1. The height is w x1 over L, right? And then that is times x1 divided by 3. Then I add m of x1, and that has to equal 0. And what you find here, if you solve for it, is m of x1 equals minus w x1 cubed divided by L. And I will go ahead and box that, right? So a couple things to point out here. First, it's now, the moment diagram is third order. So if you remember, we had a constant uniform distributed load, and our moment diagram was a parabola. Now we have a linearly increasing load, so our load is first order, so our moment diagram is third order, always 2 orders more than the than the applied load. So now we can finish this guy here. Didn't really plan out the real estate on the iPad very well, but some of the forces in the y direction equal 0. So again, the total force is this guy here, which ends up being wx squared over 2L, and it's downward, so it's negative. And then I also have a minus v of x1, and that is also downward, so that is also a negative. And then when I solve for v of x1, it is minus wx1 squared divided by 2L. And I will box that guy as well. Like that. All right. So that's our moment and shear diagrams. Now we've just got to draw them. So if I go to the new sheet here, and I will redraw the applied load like that. I guess we'll do the shear diagram in red, and we'll do the moment diagram here in blue. So this guy is the moment, this guy is the shear, and I gotta remember to show the support conditions, right? And so here the shear diagram, if we look at it, it is second order, right? And it's negative, so it's starting at 0, and then the more we move towards the right support of the diagram, the more negative it gets, right? And so it actually looks something like this, where this guy here is a parabola, right? And if you look at this amplitude, it ends up being minus WL over 2, right? And that should make some sense because that is the area of this entire load, right? That's just W, which is my height, times L, which is my base, times 1/2. Right? So let me clean that up a little bit. So that's the total shear force. That's got to be the reaction. Otherwise, we don't have equilibrium. And then from a moment standpoint, it sort of looks the same. The difference, and I am drawing it at a larger magnitude, that actually doesn't mean anything because the units are different, so you can't simply directly compare them. But this is a cubic, right? This is not a parabola. The moment is always 1 order more than the shear, because the shear is the slope of the moment diagram. Right? So if we look at the amplitude here, it turns out to be minus WL squared over 6, like that. So we've got our applied load here, linearly varying, right? So that's sort of a single, we'll call it, first order. Then the shear becomes second order, and then the moment becomes third order. Right? And actually, this, I think I have this wrong. This needs to be WL cubed. Hold on. Actually, let me double check this. No, it should be WL squared, right? Force per length, that's right. But it is varying in terms of x cubed, because the L at the bottom is just a constant that we're dividing out. So that's it.